This is lesson 9.7. I apologize. The first time through, the video was kind of a mess, so you're going to see that my notes are already done, but I'm going to explain them better. And if you need to pause after each slide, then do that just to catch up on the notes. It says Taylor polynomials and approximations. A series can be used for more than just determining its convergence or divergence. An application of series is in the approximation of a curve. A polynomial with terms generated by a series. Pause. A polynomial whose terms were created from a series can closely resemble another function's behavior on the interval, and it can match nearly identically about a point. We call this centered. So we're going to use a polynomial to approximate an original function, a polynomial that comes from a series, and you can predict what the terms are of that series. And we're going to see how the higher the degree of the polynomial, the better the approximation for that curve. But the only place at first that we can guarantee that they match is at the point that it's going to be centered around. So we're going to pick a point, and you can see in this picture there's a cubic polynomial. Here's the cubic. And that cubic is supposed to be approximating the original curve, probably the sine curve, but it's not a great approximation because you can see as we get further and further away of this point, which is where we're centered, as we get further away, the cubic is getting further and further away from the sine curve. There's going to be a lot of error. But right in this vicinity, they're pretty closely resembling one another. So the higher degree we go, the better the approximation is going to be. Case in point, if you look at the next slide, you'll see the difference between the cubic and something of the 8th degree. The cubic is only a good approximation right here. But as we increase, and this is actually zoomed in quite a bit, as we increase to the 8th degree, we not only have this small little sliver, but a good chunk of where they match each other. Well, how do we find that polynomial? The first thing we're going to do is let our constant term match. And this is all based on this centering idea, where it said that we center or expand about C. We're going to center at C. In other words, what we're going to do is we're going to pick a C value, which is a specific X value, and we're going to say the polynomial's constant at that value, the polynomial's evaluated value at that number, is going to be the same as the original function. In other words, for example, if I'm looking at the function e to the x, then the single constant term, if I'm centering at 0, is going to be this function evaluated at 0. Okay? It's the y-intercept for this particular example because at x equals 0, that's the definition of a y-intercept. Sometimes c will not be 0, sometimes c will be any other number, but for right now, that constant term, p of 0, is going to be what we get when we plug 0 into f, which is e to the x, or now e to the 0, in other words, the value 1. But what I'm going to do in this first example is not just use a constant term, but use a first-degree polynomial, otherwise known as a linear function. And a linear function is of the form y equals mx plus b. We just found the constant term, b. But in order to find the slope for that other term, how do we find a slope when it comes to looking at functions? Well, we need the derivative. So we're going to take the derivative of the function e to the x, which is still e to the x, plug in 0 and you get 1. These two numbers become the numbers that we plug into the original form of y equals mx plus b, but in this case we're using an ascending formula. So 1 goes in for the constant, 1 goes in for the coefficient of x, And we can say that e to the x, if we were to use a polynomial, a first degree polynomial to approximate e to the x, that first degree polynomial is 1 plus x. You could write x plus 1, but again, we don't usually do that. We usually build our series from the bottom up. Okay? So what are we going to be doing? Not only are we going to be creating these polynomials, but we want to see how closely they resemble graphically. In this case, how good of an approximation is that linear function 1 plus x, or p sub 1 of x? That means first degree polynomial. How good is that approximation? Well, it's only accurate pretty much right around the point that we're centered about. How do I get it to be more accurate? Well, perhaps we look at the quadratic. The quadratic approximation is found very similarly to what we've been doing all along. First, we'll evaluate the original, then we evaluate the first derivative, then we evaluate the second derivative to come up with the coefficients of each of these terms. The constant term has a coefficient of 1, or a value of 1. The first derivative's 1 degree has a coefficient of 1. And the second derivative gives us a 1 for the second degree piece of this quadratic. Well, how can I summarize the process a little bit better? Well, we're going to brainstorm here. What pattern do you see in this situation? I'm hoping you see that each of the x values is increasing by 1 in its exponent. And I'm hoping that you're seeing that the denominators are all going to be factorials. Now this is the polynomial approximation of e to the x, but that's not the polynomial approximation for every function. The question is, how did we come up with this? Where did this come from? We're actually going to skip this slide and go right to here. This is where it comes from. The Taylor polynomial approximation for any function is of the form p sub n of x equals the evaluated original term over 0 factorial, which hopefully you remember is 1. The first derivative times x minus the number we're centered about over 1 factorial, plus the second derivative times x minus c, the number we're centered about, squared over 2 factorial, And hopefully you realize that the derivative matches the exponent, which matches the denominator factorial. Now in the last example, we gave you this as a summary. And the reason that it looks like this is because we centered about the point x equals 0 or c equals 0. Probably I should write. So you're seeing x minus 0 squared, x minus 0 cubed, x minus 0 to the nth power. But because it's minus 0, it's summarized to eliminate all of those minus zeros. If we were centered about the point 2, c equals 2, then you'd see a lot of 2's being plugged in. Technically, there is a piece right here that I didn't include that says x minus c to the 0 power for the 0th term. But since we have a 0 power, it turns into 1 anyway, so that doesn't really need to be there to make it a little bit more accurate. If we're centering our polynomial about the point c equals 0, then it's what we call a Maclaurin polynomial. So in the umbrella of Taylor polynomials, the one specific c equals 0 situation is called a Maclaurin. So that's probably the more accurate way. If I say Maclaurin, you know it's a Taylor polynomial and c is 0. All right, there's steps of what to do, But instead of following just the steps, we're going to go right for the actual work. And I'm going to change this question a little bit. We're going to write find the fourth Taylor polynomial, where c equals 1. And I think, yeah, that's basically exactly what's example number 2. I just have it basically written twice, and I don't need that. So here's how we're going to find the fourth Taylor polynomial, fourth degree Taylor polynomial. If it's a fourth degree, in other words, p sub 4, then there's a constant term, and there's all the terms leading up to a fourth degree. So if there's a constant term, a first degree term, a second degree term, third and fourth, there's 5 terms, starting with the original term, and then we're going to figure out the rest of the terms by taking derivatives. Okay, so I have an original term, and then I'm going to have 4 derivatives. Once you get to 4 in your derivative succession, we start to write them as numerals inside parentheses. All right, so what's the derivative of the natural log of x? It is 1 over x. And since I'm going to be taking derivatives from here, I'm going to switch this to exponential form so that my derivatives are easier. Negative x to the negative 2, positive 2x to the negative 3, and finally negative 6x to the negative 4. These 4 derivatives generate formulas that help us figure out the coefficients of the terms of the Taylor polynomial. So if they're coefficients, then they must be evaluated numbers. Evaluated where? At c equals 1. So f of 1 would be like natural log of 1, which is 0. The derivative at 1 would be like taking, and I'm going to write these, well, I guess it really doesn't matter. What's 1 to the negative 1 power but 1? The second derivative evaluated at 1. Well, 1 to any power is going to be 1, so this now becomes negative 1. The third derivative is going to be 2. And lastly, the fourth derivative is going to be negative 6. Like I said before, these become the coefficients of the Taylor polynomial. And the Taylor polynomial is actually incredibly easy if you follow the pattern. P sub 4 of x is equivalent to saying f of 0 times x minus, in this case, 1 to the 0 over 0 factorial. Think of all the places where we just put a 0, and the next term becomes 2. Sorry, that's not 0, is it? That's supposed to be a 1. Now it's f of 1 times x minus 1 to the 1 over 1 factorial. First derivative. That's the things about. Second term is the second derivative evaluated at 1, x minus 1 squared over 2 factorial, plus the third derivative at 1 times x minus 1 cubed over 3 factorial, plus the fourth derivative times x minus, or fourth derivative at 1 of x minus 1 to the fourth over 4 factorial. I'm going to simplify what I see because I'm going to create a nice polynomial that I could easily put in a calculator from here. F of 1 is equal to 0. x minus 1 to the 0 over 0 is 1 in both of those situations. The first derivative was 1 times x minus 1 over 1 factorial, which is 1. My next coefficient is negative 1 times x minus 1 squared over 2 factorial, which is 2. My fourth coefficient here, 2 times x minus 1 cubed over 3 factorial, which is 6. And then the last one is negative 6 times x minus 1 to the 4th over 24. Okay, to summarize it even better than you see it now, p sub 4 of x, the fourth degree Taylor polynomial, is equal to, well, this is eliminated, x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3, right? The 2 and the 6 can cancel, minus x minus 1 to the 4th over 4, because the 6 and the 24 cancel. This right here, although messy and squeezed in the corner, is your fourth degree Taylor polynomial. Hopefully you can see that there is a pattern that generated from the answer. Even though it came from a pattern before, there's a new pattern that just arrived. This pattern is going to help us generate an nth Taylor polynomial if we can come up with a formula for it. For example, if I want to know the nth term, if I went out to an nth degree polynomial, the nth term is alternating. We'll talk about the exponent in a second. It's going to have x minus 1, and we know that the factorial and the degree are going to match. Since the first term here is positive, then I have to make negative 1 turn into a positive 1 somehow. You could either add 1 or subtract 1 to its exponent. Okay? That nth term helps us create what we're going to learn later in this chapter as a Taylor series. The Taylor series is the formula that generates all of the terms in the polynomial. And that would be if we went from 1 to infinity of the nth term that we just came up with the formula for. Okay, so this is foreshadowing to section, I want to say 9.9. That formula generates the terms, and we only needed 4 of them for the fourth degree. But if I wanted, say, the 10th degree Taylor polynomial, I would follow that formula and fill out all 10 of these with their pattern. Okay? Moving on. Find the third degree Taylor polynomial of sine x. The c value that we're given is pi over 6. So if I'm finding the third Taylor polynomial, then it should be no surprise that I'm going to have to do 3 derivatives. If you need to do your code off to the side, that's fine, but the derivative of sine is cosine. Cosine becomes negative sine becomes negative cosine. Pi over 6, if you multiply by 180 over pi, is 30 degrees. So I'm going to be evaluating both sines and cosines at 30 degrees, which is why I have my little codes up here as reminders. Okay, 3 derivatives, because I'm looking at the third degree polynomial. This is going to be the constant, and these are the coefficients of the successive increasing terms of that polynomial. The formula, excuse me, The formula is no different than before. The Taylor polynomial always has an x minus c raised to the power of the placement that you currently are. So if we're at the 0th term or the constant term, it's going to have a 0 here and at the bottom. The next term, which is the linear term, has a 1 and a 1. The quadratic term has a 2 and a 2, and the cubic term has a 3 and 3. My job at this point was to just simplify what I see. I changed all of my factorials to what they actually are. Remember, they're just multiplying down from that number down to 1. So like 3 factorial is 3 times 2 times 1. And if you're unsure, you can always take that number. Probably can't see it. There we go. Factorial is found in the math button over on the probability side. And it's the 4th thing down. So there's the evaluated factorial. And when all is said and done and everything is finally simplified, my 3rd degree Taylor polynomial is 1/2 plus the square root of 3 over 2 times x minus pi over 6 minus 1/4 x minus pi over 6 squared minus square root of 3 over 12 x minus pi over 6 cubed. Whether or not you put the x minus pi over 6 in the numerator with what's already there, that's up to you. Sometimes I do, sometimes I don't. All right. Number 5, the nth Maclaurin polynomial. So here's what that means to me. First of all, Maclaurin polynomial automatically implies that C is 0. The nth Maclaurin polynomial implies that there must be a pattern that's going to allow me to summarize that term like we did in the last example prior to this one. Sorry. So I don't know how many of these derivatives I'm going to have to take before I see a pattern, but usually what I'll do is start with 4 derivatives, and if I need to go further out, I will. But you're going to see real quick that it only takes 1 or 2 of these to realize that the pattern is very, very easy to remember. E to the x becomes e to the x no matter what derivative you're doing, since your exponent is x and there's no chain rule involved. If I evaluate all of them at 0, I end up getting 1. So what that means to me is the constant term is 1, and the coefficients to every term after that is going to also be 1. Well, what's going to go in the parentheses? Since it's a Taylor polynomial, you're going to see x minus 0. Those exponents are going to increase with matching factorials in the denominator. So all I did to finish this question was get rid of the minus zeros because they were irrelevant and just summarize it to the nth degree. This last term, the last term of any nth degree Taylor polynomial, is the formula that you would use for your Taylor series. So this is technically a Taylor series from 1 to n. Okay? This picture was not done well because it's not in color, but it's just kind of a reiteration that the first approximation was this line, and it was a terrible approximation. The quadratic was a little better, the cubic better than that. This one right here, this horizontal line, was a constant approximation. It's a constant of y equals 1. That's a terrible approximation because it only matches e to the x at that point. This was your first degree, 1 plus x. I feel like this is e to the x. This was probably a very wide second degree. Okay, so that makes the cubic the light one in the middle, which is what we just found, x, 1 plus x squared over 2, and then x cubed over 6. Okay, so they're getting closer and closer to hugging the original graph a little bit more, but certainly having a better or a larger degree would be a better approximation. All right, this next one is a little messy, so I'm going to do it on a separate sheet of paper and have you just follow my work from there. Find the nth Maclaurin polynomial for cosine of x. And then we're going to summarize it in sigma notation. All right. As soon as I see Maclaurin polynomial, I know that c is 0. I also know that because it says the nth degree, I'm going to have to go as many terms out or as many derivatives out before I see a pattern. And I think we've done derivatives of sines and cosines enough to know that it's not until 4 times through the cycle that we end up back where we started. But let's pretend that you didn't know that. I told you already that if I'm not quite sure, I usually go 4 out. Okay, first I'm going to look at just the function itself, and then I'll worry about evaluating that function. Okay. The original is cosine. Its derivative is negative sine, followed by negative cosine, followed by sine, followed by cosine, and we see that the pattern starts to repeat at that point. Then it's important to go through and evaluate each of these at 0 because that's going to in turn become the coefficient of our polynomial, or the coefficients of our polynomial. Okay. If you're not sure about sine and cosine at 0, you can either use the chart that I introduced you to, or looking at the unit circle, at 0 degrees, we've got the point 0, 1. 0, or I'm sorry, not 0, 1. Duh! My goodness gracious. 1, 0. The x value is your cosine, and the y value is your sine. Sorry about that, guys. Okay, so at 0, cosine is 1. At 0, sine is negative 0, which is 0. At 0, cosine would be 1, but now it's negative 1. Your sines are 0, and cosine again repeats and ends up as a 1. So here's what I know, super easy to put together. The nth degree Maclaurin polynomial is going to be the evaluated number times x minus your c value to 0 over 0 factorial. Keep going. Next term, x minus 0, 1, and 1. Next term, x minus 0, 2, and 2. Next term, x minus 0, 3, and 3. Next term, x minus 0, 4, and 4. And then I'm going to do dot, dot, dot. And hopefully I end up seeing a pattern with what I have in front of me. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and then 6, and then 24. My nth degree Taylor polynomial is x minus 0 to the 0, which is 1. All of these that have 0 as a coefficient go away, and I have negative x squared over 2 plus x to the 4th over 24. Hopefully you know what's going to come next. And I'm going to write down one more term just as predictive, just to be predictive. We know that it's going to be x to the, well, let's see. First of all, I know that it's negative because we're alternating. Positive, negative, positive, negative. This is x to the 0, x squared, x to the 4th, followed by x to the 6th. Now, how does the denominator come from the numerator? Well, If you remember, this was 4 factorial, so this has to be 6 factorial, which is, grab that, I'm just going to put 6 in its place, 720. And hopefully what I just went through will help us figure out the formula here. We know it's alternating. We know it's x to something over that something factorial. Well, what are the exponents? What do they have in common? 0, 2, 4, 6. Hopefully you realize they're even numbers. But they're even numbers that started at 0. Okay? So if I want the nth term, if 0 has my first term of the polynomial, then my nth term isn't going to be twice that. Okay, let me rephrase this. My third term doesn't have a 3 over 3 factorial, right? My fourth term doesn't have a 4 over 4 factorial. So we need to figure out what that number placement is in comparison. It's not double where we're at. I always start with 1 minus, and then if that doesn't work, then I'm going to do plus in its place. But let's see. If I plug in 1, do I get 0? If I plug in 2, do I get this? If I plug in 2, yep. If I plug in 3 for my third term, do I get a 4? If I plug in 3, then this becomes 3 minus 2 times 2, which is 4. If I plug in 4, do I get 6? 4 minus 1 is 3 times 2 is 6. Yes, so that formula worked. It can't be 2n because you wouldn't get 0 for your exponent and this denominator if you plugged in 0 right away. So we had to manipulate our positioning by adjusting the n value. If n doesn't work, then either subtract 1 or add 1, and you can figure it out from there. I also know that this denominator has to match that. But right now that factorial is only touching the n minus 1. I need it to touch all of it, so I'm going to put it in parentheses. Now the other thing I need to keep in mind is this alternating piece. If I'm starting with a positive number, then I'm not going to have just n be my exponent, but n plus 1. You can also use like n minus 1. That's fine too. N plus 1 and n minus 1 are going to give you the same placement in an alternating series. So if this is my nth term, okay, this is the nth polynomial, then if it says to write it in sigma notation, then my Taylor series, or my Maclaurin series in this case, for a cosine curve is just that last term written in summation form. Okay, nth degree Taylor polynomial followed by the Taylor series, or better yet, the nth degree Maclaurin polynomial, because I'm centered at 0, and the Maclaurin series. Okay. The last portion of this lesson talks about error. And my first time through discussing this, it was a total mess. So what I'm going to do is end the video right now, and then if I have to re-record my remainder discussion, I'll just do that. So here's your first lesson finished.